Transmitting electrical energy from Columbia River dams calls for a wide variety of engineering skills. Thousands of miles of high-voltage circuits already link the generators of Bonneville and Grand Coulee, load centers of the Pacific Northwest. And as the new dams are completed, the men who design and construct the substations and transmission lines must keep pace with the ever-growing power needs of the region. New lines must be surveyed, the right-of-way cleared, structures erected, and conductor installed to deliver the millions of kilowatts of new energy from America's greatest power stream. In this film, we shall be concerned with but one phase of this complex operation, the installation conductor, the material which will actually carry electrical energy. This job calls for close engineering teamwork, design, material, and workmanship that add up to efficient, economical service. A wide variety of types and sizes of conductor is available. The two types most commonly used in high-voltage transmission are stranded copper and stranded aluminum, the latter usually reinforced with a core of galvanized steel. There are a number of other types of conductor designed for special purposes. All aluminum conductor can be used in situations where high tensile strength isn't important. When extreme strength is needed, copper-clad steel may be used. This conductor is made up of steel strands coated with copper by a molten weld process. Another type uses copper strands around a copper-clad steel core. Expanded copper is available in several designs, either with or without steel reinforcement. The choice of conductor material in each situation depends on several factors: the amount of power to be transmitted, the voltage to be used, the distance the power is to be transmitted, the mechanical stress to which the conductor will be subjected due to terrain and climatic conditions, and comparative cost. Copper has the best electrical conductivity of conductors commonly used in transmission lines. But for high-voltage transmission, aluminum has become popular in recent years because of its lightness, increasing availability, and favorable price. Because of aluminum's lower conductivity, somewhat larger sizes must be used than if copper were chosen. And because of its lower tensile strength, a steel core is used in situations where reinforcement would not be necessary for copper. A typical conductor used on Columbia River System 230,000 volt lines is ACSR, aluminum conductor steel reinforced, with 795,000 circular mils of aluminum. This material has a copper equivalent of 500,000 circular mils. That is, its carrying capacity is equal to an unreinforced stranded copper conductor of 500,000 circular mils. The greater size of the ACSR gives it one advantage. There is less power loss due to corona, a discharge into the air that occurs at high voltage. To meet the corona problem with copper, expanded conductors have been designed. In making a choice of conductor materials, several properties, in addition to capacity and diameter, must be taken into consideration. An important one is the ratio between strength and weight. Let's go back to our examples of ACSR and copper of equal carrying capacity. We find that the ACSR has a breaking strength, that is, the tension it will stand before it breaks, of 31,200 pounds, as compared with 22,510 pounds for the non-reinforced copper. The weight of 1,000 feet of ACSR in this particular size and design is 1,098 pounds, compared with 1,544 pounds for the same length of the equivalent copper. In other words, the ACSR in this particular case is both stronger and lighter than the smaller diametered copper of the same carrying capacity. Actually, the choice of conductor material isn't quite that simple. We have to consider such things as the added weight of ice, a half-inch coating throughout most of the Pacific Northwest, and up to a full inch or more where winters are unusually severe. Then there is the added force of wind, which can reach velocities as high as 100 miles per hour in some localities. Let's follow through with the same examples and see how the design engineer uses vector diagrams in making a choice of materials. First, to the weight of 1,000 feet of bare conductor, we must add the corresponding weight of a half-inch coating of radial ice, or 1,005 pounds for ACSR and 822 pounds for the equivalent copper. Second, we must add to the combined weight of conductor and ice the horizontal force that a 60-mile-an-hour wind will exert on 1,000 feet of the iced conductor, or 1,405 pounds for ACSR and 1,210 pounds for the equivalent copper. Completing our vector diagrams and checking the resultant components, we find the total effective weight under maximum ice and wind loads for 1,000 feet of conductor is 2,529 pounds for ACSR and 2,657 pounds for the equivalent copper. Note that the ACSR has now lost most of its weight advantage because its larger diameter gave it both a larger ice and wind load. Similar diagrams can be plotted for any maximum ice and wind loadings expected in the area in which the line is to be built. For example, plotting vectors for 1-inch ice loadings and 60-mile-an-hour winds gives us resultant components of 4,270 pounds for ACSR and 4,248 pounds for copper. The weight advantage is now slightly in favor of copper. However, we are concerned not with weight alone, but with the strength-weight ratio of the conductors. Even though one conductor under a given set of conditions may be heavier than another, if it is also stronger, the additional strength may overcome the weight disadvantage. Here's why. A free-hanging, flexible body, such as a conductor, describes what we call a catenary curve. The sag of a catenary is the measure of the greatest vertical distance between the free-hanging material and a straight line between its supports. The comparative sag characteristics of two conductors may be reduced to a simple formula: strength over weight. As you know, if you've ever put up a clothesline, the tighter the catenary is drawn, in other words, the less the sag, the greater the strain on the supporting structures. Suppose, for example, we were to substitute for a given conductor another one of twice the strength. Then the stringing tension could be doubled and the sag cut in half, assuming, of course, that there would be no change in weight. If, however, the second conductor were also twice as heavy, the sag would return to its original value. In other words, changing the strength and corresponding tension and weight by the same percentage causes no change in their ratio and consequently no change in the conductor sag. Now, going back to the two conductors we were discussing, we found that the breaking strength of the ACSR in our example is 31,200 pounds compared with 22,510 pounds for non-reinforced copper of equal electrical capacity. Dividing these strength values by their corresponding weight components of 4,270 pounds and 4,248 pounds respectively for 1-inch ice loads and 60-mile-an-hour winds, we arrive at their corresponding strength over weight ratios. We find that for the given ice and wind conditions, the strength-over-weight ratio of the 795,000 circular mil ACSR conductor is 7.3, compared with the 5.3 for the 500,000 circular mil non-reinforced copper, a decided sag advantage for the ACSR if the lines are to be strung to the maximum tension permitted by the conductor strength. This advantage, however, could be overcome by using reinforced copper. Or maximum tension may be limited by the strength of the supporting towers rather than that of the conductor. Then either material could be used, and the final determination would be on a basis of comparative cost. Wherever feasible, specifications are such that more than one material could be used, thus giving the advantage of competitive bidding not between manufacturers of the same material, but also between competitive materials. What does all this mean in terms of practical transmission line design and construction? In transmission design, one of our considerations is providing the necessary clearance between the conductor and the ground or other obstructions over which the line must pass. It is only reasonable that a conductor which is stronger or lighter, or both, can be drawn up to a higher sag and still keep the strain within safe limits. This means that with a stronger or lighter conductor, we can use lower towers or longer spans, in either case effecting substantial economies. Elimination of one steel tower can mean a saving of as much as $10,000. A member of the office engineering staff, commonly known as the sagger, is the fellow who determines the sag for each span. In plotting sags, he uses a simple but ingenious gadget called a conductor sag template. Separate templates are made for each type of conductor and design load. The upper curve of the template represents the maximum sag for a particular conductor with a given combination of maximum tension and ice and wind loading. The vertical distance between the edges of the template represents the minimum clearance specified for the voltage being used. The template is used over a profile map of the right-of-way. Both template and map have a vertical exaggeration of 10:1. The sagger determines both the height and location of the supporting towers or poles. The map shows not only the profile of the land, but all other physical features, such as rivers, highways, railways, telephone lines, and other power lines. The sagger must be sure the sag provides the required minimum clearance in each case. He must also consider state and federal safety codes, and in the case of navigable rivers, special crossing permits and instructions must be followed. As the sagging engineer proceeds with his job, other members of the office staff prepare the other necessary design data and instructions for all phases of transmission line construction: preparation of the right-of-way, erection of towers, and installation of conductor. This material is assembled into convenient books. These books contain the basic engineering data to be used in the actual construction of the line. In the field, another engineering staff is responsible for seeing that all work done by contractors conforms to specifications. In planning the stringing operation, one of the first steps is to spot the points to which conductor will be delivered. Conductor comes from the manufacturers in reels of varying lengths, and one of the field jobs is to select the point along the right-of-way to which each set of reels of approximately equal length will be delivered, considering such factors as length of spans and location of access roads and dead-end structures. Incidentally, a dead-end structure is a tower or pole to which the end of a length of conductor is anchored, usually at points of heavy strain, such as sharp changes in direction, or at the end of extremely long spans. It may be either a self-supporting tower or a guide pole structure of steel or wood. A suspension structure is one which supports the conductor at an intermediate point, usually along a straight section of line. Reels are hauled to the designated spots for unloading. They may be placed on simple wood horses or preferably on more elaborate trailer-mounted reel jacks with braking devices. In either case, the reels are opened and wire mesh fasteners known as stringing socks are used to attach the ends of the conductor to steel cables called sock lines. In a typical situation, a crawler tractor is used, unreeling 3 or in some cases as many as 6 or 7 conductors at once. Meanwhile, another crew has been busy preparing the suspension towers for stringing. Large pulleys known as shibs are fitted with light ropes called finger lines. They are hoisted and fastened to the insulator strings, which have already been permanently secured to the towers. As each tower is reached, the sock lines are disconnected from the tractor and pulled through the shibs by means of the finger lines. The design of the sock makes it possible to pull the end of the conductor through the shib without difficulty. This process is repeated at each tower until the conductor reels are empty or the next dead end is reached. Conductor, being a fairly soft material, must be protected from abrasion against rocks, other hard surfaces. When this cannot be done by keeping it off the ground by tension, it is lagged by permitting it to run over boards, poles, logs, stumps, or other soft material as available. When a line must be strung across an obstruction, such as a highway, railroad, or other power line, crossing guards are used. These are temporary wood pole structures fitted with shivs to support the conductor while it is being pulled through. Y-arms are usually fitted below the shivs for added protection. This method makes it possible to cross busy highways without disrupting traffic or even live power lines when necessary. Since it may be several miles between dead ends, splices are frequently required. When splicing ACSR, the aluminum strands are removed to expose several inches of steel core. Compression fittings of the same material as the conductor are used. An aluminum sleeve fits over the outer strands and a smaller steel sleeve over the steel core. Conductors without steel cores require only the outer sleeve. A hydraulic press exerting up to 100 tons of total pressure compresses the steel sleeve around the core until the two become, for all practical purposes, one homogeneous mass of metal. Dies of very hard steel are used, accurately designed for each size and type of conductor. With the steel sleeve pressed on, the aluminum sleeve is accurately centered over the compressed steel assembly, and zinc chromate paste is injected to prevent corrosion. With a different die in the press, the aluminum sleeve is pressed on over the steel sleeve and the ends of the conductor. So here's what we have. First, the ends of the steel core are exposed. The steel sleeve is pressed on. The aluminum sleeve goes over the compressed steel sleeve and the outer aluminum strands. And the result is a splice as mechanically strong and electrically efficient as the rest of the conductor. When the stringing operation has been completed, we have a section of line with the conductor hanging loosely in the shibs. The next operation is sagging. That is, pulling the conductor up to the sag specified in the stringing manual. Before the line is sagged, it must be made fast at one end. In most situations, this can be done by securing it permanently to a dead-end tower. Insulators designed to meet the electrical and mechanical requirements of the particular situation are assembled. Again, compression fittings are used. Steel and aluminum dead-end bodies, similar to the compression joints used on splices, secure the end of the ACSR conductor to the insulator string. They are pressed on in the same way. The dead-end body has a clevis end for attaching it to the insulator string. The usual procedure is to hoist the entire dead-end assembly, conductor with dead-end fittings and insulators, at one time. With one end of the conductor made fast to the tower, a job of pulling it up to sag can begin. A truck-mounted winch is usually used, and several miles of line can be sagged in one operation, if distances between dead ends permit. At 2 or 3 of the longer and more level spans, transits are set up to check the sag. Sometimes the transit is set up on the ground, or in other cases it may be mounted on the tower. There are 3 methods of determining conductor position when at proper sag. The transit may be set at a point level with the lowest point on the conductor when at proper sag. The line of sight may be a target set at a predetermined elevation on the opposite tower. The line of sight may be set at a calculated vertical angle from any convenient transit location at the tower. Temperature must be carefully checked because the length of the conductor and its corresponding sag increase with heat. Corrections are made to cover the range of temperatures expected during the day. In this particular case, where the calculated angle method is being used, the angle for 60 degrees Fahrenheit is 0 degrees and 17 minutes. So, a transit is set accordingly. With all preparations made, the sagging operation begins with crew members communicating by telephone or radio. Up it goes until on sag here. Usually all of the spans won't come up to the proper sag on the first pull because of the cumulative effect of friction in the shivs. This is adjusted by running the conductor back and forth for a few feet several times. The section of conductor being sagged may run to a dead-end tower, or as here, it may be fastened at an intermediate point by a temporary snub until the next section is sagged. At the end of the sagging operation, we have the conductor secured at both ends, but still hanging from the shivs at the suspension towers in between. The next job is clipping, removing the conductor from the shivs and attaching it to the insulator. This is one of the most spectacular jobs in transmission line construction. Linemen must do their work on ladders suspended in midair, often 100 feet or more above the ground. Hand-operated hoists are used to lift the conductor from the shiv. The shiv is lowered, and bundles of tapered armor rod, which have already been assembled on the ground, are hoisted and placed around the conductor. The purpose of armorization is to minimize the effects of vibration and to protect the conductor from damage by lightning or abrasion from the clamp which secures it to the insulator. The rods are twisted around the conductor and the clamp fastened around the rods and attached to the insulator string. In mountainous terrain, stringing is complicated by the tendency of the conductor to run downhill. In general, when the conductor is in the shivs under these conditions, there will be too little sag in the upper spans and too much in the lower ones. The necessary correction is computed mathematically and then allowed for at the time of sagging. Before the conductor is clipped, however, it must be pulled into the correct position. The correction is made by means of what we call offsets. With the conductor at rest in the shivs, the lineman measures back or ahead a predetermined distance from the spot on the conductor directly below the cross-arm support, and the insulator string is clipped in at this measured point. This correction may be as much as 10 feet in extremely rough country. Notice how the insulator string drops back into a vertical position as the hoist is released. A final twisting of the armor rod completes the clipping operation. As a result of precise engineering and careful workmanship, the suspension insulators of a properly constructed line will hang in a perfectly vertical position. Horizontal forces are in balance, and the only strain on insulator and tower is the vertical pull of gravity. One more job remains, bridging the gap in the circuit at the dead-end towers. Short lengths of conductor, called jumpers, are fitted with compression fittings and bolted to lugs provided for the purpose on the dead-end bodies, completing the circuit. We have seen a number of the important steps involved in stringing and sagging a high-voltage transmission line. Details will vary according to such factors as the type of equipment available to the contractor and special problems brought about by peculiarities of the terrain. But the same general techniques will apply. Techniques which are the sum of many skills and the product of many years of research and experience in building the high lines that carry the vast and inexhaustible energy of the mighty Columbia River to the cities, the farms, the factories, and the homes of the Pacific Northwest.